I continue to work on problems that are exactly like problems that you're going to encounter on the exams. These problems come from problem set number 4. And so the first problem that I'm going to work on here is problem number 2 of the problem set number 4 set of problems. This is a problem that requires us to understand both Newton's second law, which is force equals mass times acceleration, and it also means that we need to understand Newton's third law, which is for every action there's an equal and opposite reaction. So what I'm going to do is I'm going to illustrate there's going to be 3 masses as you see here, and the first mass M1 equals 1.0 kilograms. The second mass M2 equals 2.0 kilograms, and the third mass M3 equals 3.0 kilograms. And what's going to happen is, if you can imagine representing all 3 of these masses is just a single supermass where I have my M total represented by that dot, which is simply equal to M1 plus M2 plus M3. So if you can imagine all 3 of those masses represented by a single dot, what's happening is that there's some external force that's being applied, and that external force is equal to 12 newtons. So I want to show you how we can think of both all 3 masses moving to the right with some external force of 12 newtons, and to what extent that entire system is going to accelerate. But then I'm also going to break it down into how all of the individual masses experience forces, some of which are action-reaction pairs. And so it's always a good habit when you think of a mass and you think of forces acting on that mass. I'm going to start with M1. M1, the external force of 12 newtons gets applied to it. That's the mass on the far left, where if you can imagine like a hand pushing on these blocks, it's mass 1 that the hand touches. And so I'm going to mark this as F external. And when I say external, I mean external to the system of the 3 blocks. It's not blocks exerting forces on each other, but it's some other force acting on the blocks, and it happens to be acting on the block on the far left, the M1, which is 1 kilogram. Now, when that block M1 gets pushed into M2, this is where we're going to have our first action-reaction pair. If M1 pushes into M2, M2 is going to push back on to M1. And so what I'm going to do is I'm going to draw a force acting in the opposite direction, and I'm going to use the nomenclature of the force acting on mass 1, that's my first index, comma, by the second mass. So that's why I call it F12. So to the right, you have the external force being applied. You can imagine it's like a hand pushing to the right. It makes mass 1 push against mass 2. Mass 2 pushes back against mass 1. That's what we have for F12. That's the force on 1 from 2. We can do the same thing for the mass 2. And remember, all of these blocks are touching each other. So mass 2 pushed back on mass 1. That's what our F12 is. But we also have the force from mass 1 pushing on mass 2. That's what made mass 2 push back on mass 1. So we can think of, to the right, when it comes to mass 2, we can think of the force on 2 from 1. So this right here is an action-reaction pair with this force right here. Those forces are equal and opposite each other. Now mass 2 is going to push against mass 3, and so you can think of the force on 2 from 3, and that's going to the left. So I'm going to say force on 2 from 3. And now completing the picture, I also want to draw a free body diagram for mass 3. For mass 3, it feels mass 2 pushing up against it. The force it feels pushing up against it from mass 2 goes to the right. We call this the force on 3 from 2. So this force on 3 from 2, that's equal and opposite the force on 2 from 3. This is a Newton's third law pair. Just like the force on 2 from 1 is opposite the force on 1 from 2. Those are equal and opposite. So originally we had an external force on the first mass, and you can imagine the masses bumping against each other, the force propagates through. So by the time we get to this third mass over here, the only force that's acting on it is the force on 3, that's the force on block 3 from block 2. That's the blue block, okay? And the red block pushing against it. Not the external force. That was applied back at mass 1. So the picture that we have here is that the force exerted on the third block by the second block must be the force that's accelerating the third block. As you can imagine, going back to this picture right here, if you think of all three masses as like this supermass where you add the masses together, there's a single external force. It's going to accelerate this mass system to the right. Well, since we know these blocks are accelerating to the right, by our free body diagram, what's making the blue block, block 3, accelerate to the right is actually the force on it from the red block, block 2, next to it. So really quickly, I'm going to solve for what the acceleration of the system is because these blocks are together. They're end to end in a line, and they're moving to the right. And so they all are moving at the same acceleration. And by that I mean that if I apply some external force, which in this case is 12 newtons, that's equal to the mass total of the system multiplied by the acceleration total of the system. Again, this is just Newton's second law. What I'm drawing right now is this picture right here, where you can think of this supermass being the sum of the masses, having a 12 Newton force applied, and it's going to accelerate all three of the masses by the same degree. And so this means that I can rewrite this using algebra as A total is equal to the external force applied, again that's 12 newtons, divided by M total. And I already expressed M total, right? That's just the sum of our masses. And so this is going to be equal to 12 newtons, that's the external force, divided by 1 kilogram plus 2 kilograms plus 3 kilograms. 1 plus 2 plus 3 is 6. And so this is going to be equal to 12 newtons divided by 6 kilograms. And so this is equal to 2.00. Take your answers out to 2 decimal places on exams. Meters per second squared. That's the acceleration that every single one of those blocks is moving at. Since we know the acceleration every single one of those blocks is moving at, we can then go to the individual free body diagrams for each block and figure out what individual forces on those individual masses are. So in part A of this problem, they want us to determine what is the force on block 3 from block 2. Again, the nomenclature. The first index is the force of the object being acted upon. The second is the object acting upon that object. So what is F32? So if I go back to this picture right here, I just got a single force going to the right, and that's going to be equal to the mass, which in this case is M3, which is 3 kilograms, and the acceleration. And again, the acceleration is the same for all three blocks. I just solved for it. It's just 2 meters per second. And so this F32, again, this is going to be the force that has to accelerate this third block alone. It's the only force we have in our free body diagram for the third block. So this means that the F on 3 from 2 must be the mass of 3. Okay. So I'm going to do that in blue to stay with my color coding here. And then it's going to be multiplied by the A total, because the acceleration total for the total system is the same as acceleration for each of the individual blocks. I already solved for the A total, and so this is just going to be equal to 3.0 kilograms multiplied by, remember I just solved for the acceleration total, which is acceleration of each of the individual blocks. That's 2.00 meters per second squared. And this gives me an answer of 6.00 newtons. Again, I'm taking my answer out to 2 decimal places. That's the force on 3 from 2. That's the only force that 3 is experiencing. There's like a chain reaction, and many of the key pieces in this story are action-reaction pairs. Again, just to kind of follow this chain reaction, 3 masses are lined up. An external force acts to the right on mass 1. That presses mass 1 against mass 2, which has an action reaction of mass 2 pressing against mass 1. So you have an action reaction of F on 1 from 2 and F on 2 from 1. Those are equal and opposite. The mass 2 then presses against mass 3, which presses back against mass 2. And that's why you have an F2-3 and an F3-2. Those are also action-reaction pairs. So when you work out the free body diagrams from all 3, you actually see that the third mass is being accelerated to the right by the force from mass 2 next to it, not from that original external force. There was a propagation through the system. Part B of this problem number 2 in problem set number 4 asks for what is the force on 1 from 2. Okay, what is the force on block 1 from the block 2 next to it? This is the picture right here. So we have 2 forces in this particular case. If we let positive piece to the right, as we typically do, then we are going to have the external force being positive to the right, that's this right here, minus the force on 1 from 2. Those are the 2 forces acting. They're both horizontal. One's positive to the right, one's negative to the left. And by Newton's second law, not Newton's third law. Newton's third law is the action-reaction pairs. Newton's second law is the mass, and just to be consistent with our color, mass 1 times the acceleration total. Because again, the total acceleration of the system is acceleration of each individual blocks. I want to solve for F12, so I can do some algebra where I add F12 to both sides. And what that leaves me with is an F on 1 from 2 that's equal to the external force, that's the 12 Newton force, minus M1 A total. And remember, we have these values already. That's 12 newtons. And this is 1.0 kilograms. And our A total, we calculated right here, that's 2.00 meters per second squared. So we're going to get 12 minus 2 equals 10 newtons. So that's how you solve for B. And you could do that for, like, for instance, like if it wanted instead for us to figure out like what is the force on 2 from 3, right? Like if they wanted us to solve for this one right here, then I would look at the free body diagram there. I'd say F21 minus F23 equals M2A total. And then I would rewrite the equation to isolate for F23, just like I did in part B when I isolated for F12. So just to review, Newton's second law and Newton's third law are both really important here. We can think of a system as having a single external force acting on it, where the mass of the system is a superposition of the mass of all the individual constituents. And so that's where this picture came from, where I can think of the three masses making a supermass of m1 plus m2 plus m3 and a single external force being applied to the right. That allows us, by Newton's second law, right, F external equals m total a total, that allows us to solve for the acceleration of the system, which happens to be the acceleration for each of the individual blocks, because they continue touching each other and moving together. Once I solve for the acceleration of the system and therefore acceleration of each individual block, I can go back to the individual free body diagrams and, by Newton's second law, solve for the forces acting on them. And as I showed you, it's a collection of forces. There's a lot of action-reaction pairs. It's like a chain reaction. It starts with an external force to the right on mass 1, but then mass 1 exerts a force on mass 2, which exerts a force back on mass 1. And then mass 2 exerts a force on mass 3, but that mass 3 exerts a force back on mass 2. So knowing A total and the masses of each objects, I go through and I show you how you can calculate some of the other forces in this chain reaction that ultimately manifests in a force being applied on block 1, but eventually we're going to see that when it comes to mass 3, it's actually a force from its next door neighbor, mass 2, that is going to accelerate the third block alone. This was problem number 2 in problem set number 4. Quick addendum, just to avoid any possible confusion. I referred to free body diagrams a lot when solving this problem, but you'll notice that I just focused on the forces that were acting in the horizontal direction. To be clear, with free body diagrams, you can also look at the forces that are acting in the vertical direction. I chose not to focus on it because the vertical forces cancel out and have no consequence in this problem, but just to be thorough, let's go back to our original mass 1. And if I wanted to talk about the vertical forces, and you can imagine this mass is sitting on, say, a table, then that mass, because it has mass, is also going to have a gravitational force of m1g acting downward towards the center of the Earth. And because there's a table getting in the way of keeping the mass from accelerating towards the center of the Earth, you can also think of having a normal force. This is problem number 5 from problem set 4. There's going to be an exam problem exactly like this. This is a problem where you have a pulley, but we are told that this pulley is massless, frictionless, and stationary. By stationary, it means it's not moving, say, left to right or up and down, but you can very much have the rope move over it. And that's what's happening in this case. This is a problem where we're going to use free body diagrams and we're going to include tension. And with an ideal rope or string, we're going to take advantage of the fact that the tension is uniformly distributed through that ideal rope or string. In this problem, we've got 2 masses hanging, and we are told that one of the masses has 2 kilograms of mass and it accelerates downward at 3,4 g. So what I'm going to do is I'm going to assume that the mass on the right is going to be the 2 kilogram. So I'm going to say m2 equals 2.0 kilograms. And I'm going to say that a2 is equal to, and let's go ahead and make, with our typical coordinate systems, positive x to the right, positive y to the left. If this is the mass that's going down, and by the way, I could have drawn this where I had m2 on the other side going down and I would get the same result, but just the way I've drawn things up, I'm going to assume that the mass that's going downward is on the right, and since the tension is uniformly preserved through the rope, mass 1 is going to be accelerating up. It's going to have the same acceleration up as mass 2 has the acceleration going down. You can imagine the distance between the 2 masses, the length of the rope is going to remain the same. It's not going to stretch or scrunch up. And so then I know if mass 2 has an acceleration downward by a certain amount then mass 1 is going upward by the same amount, so that the distance between them, the tension in the rope, remains the same. So by the conventional up is positive and down is negative, then if I'm told that one of these masses, and I'm letting this be mass 2, is accelerating downward, that means that it's negative 3 force g. So if I go over on the other side, I have mass 1, and we are going to need to solve for mass 1. And the acceleration is just going to be equal and opposite. So this is going to be positive 3 force g. This is where it's going to be helpful to make our free body diagrams. I'm going to start with mass 1. So mass 1 is this blue dot, imagine. You could imagine the mass is concentrated in that single point in space. There's going to be the force of gravity, m1g, acting down. There's also going to be what I'm calling T1, and T1 is the tension in that rope pulling upward. There are no horizontal forces acting in this problem. When I sum the forces in the y direction, I get positive T1 because upward is positive y, minus m1g is equal to m1 times the acceleration in the y direction. Similarly, I can do a free body diagram for m2. M2 also has gravity accelerating it downward, and so we're going to call this M2G, and it's down. It also feels tension, which I will call T2, and that's from the rope. So the sum of the forces in the y are T2 minus M2G equals M2AY. Remember, we already know what AY is. That's this right here. It's 3 force G downward. So that's going to come in handy. So now what we need to do is some algebra. And the key move here is that because it's an ideal rope, the tension is preserved throughout, which is to say that the tension 1, which is the upward tensional force on mass 1, that's equal to the tensional force T2, which is the upward tensional force on mass 2. So what I'm going to do is I'm going to take both of these equations and I'm going to rewrite them in terms of the tension. So for this one, what I would do is I would add m1g to both sides, which would tell me that T1 is equal to m1 AY plus m1 G. Do you see how there's an m1 in both of those terms? So I can factor out an m1 so that it's just AY plus G. And remember, the acceleration of the mass 1 is going to be the same as the acceleration of mass 2 because the distance between them, the tension in the rope, is going to remain the same. And so if mass 2 has an acceleration downward of negative 3 force G, then mass 1 has an acceleration upwards of positive 3 force G. So this equals m1 3/4 G plus G. You can think of G as 4/4G. So 3/4 G plus 4/4G is equal to 7/4G. So you can think of M1 7/4G. That is the expression for T1. And I can do the same thing for T2. I can add an M2G to both sides, so I'll have an M2AY plus M2G. Again, I can factor out an M2 because it hits both of the terms, so I can say M2 multiplied by the sum of AY plus G. The acceleration in the y direction for the second mass is -3/4 G. So you can think of this as M2 times -3/4 G plus G. So this is -3/4 G plus 4/4G. So this is going to be equal to M2 times 1/4G. So I took my free body diagrams for both masses. I could just focus on the vertical forces. There's no horizontal forces acting here. And I rewrote the equations. So I have one equation that's an expression for T1, and I have another expression for T2. But here's the key. Because it's an ideal rope, the tension is preserved throughout the rope. So what I can do is I can say that T1 equals T2. The tension is preserved throughout the rope. Now I can use this expression and this expression, and I can set them equal to each other. Because T1 equals T2, what this means is the first mass times 7/4G equals, okay, remember that's T1, the second mass, M2, is 1/4G. And remember, we are told what the second mass is. It's 2 kilograms. So now what we want to do is we want to solve for the first mass. And we have an expression where we've got M1 times 7/4G is equal to M2 times 1/4 G. We know what G is. We know what M2 is. So we just simply need to isolate M1 and we're good to go. And to do that, if I have 7/4 G, that's the same thing as 7G/4, or if we just want to divide by the whole thing, we can just say M1 equals M2, and then that's going to be the quantity G/4 divided by 7G/4. The 4's are going to cancel. The G's cancel. And I end up getting M2 multiplied by 1/7, which is to say that mass 1 is 1/7 the mass of mass 2. And remember, mass 2 is 2 kilograms. So you would simply take 2 kilograms and multiply it by 1/7, and that would give you mass 1. So I want to review this problem. You can assume that the rope can move over the pulley, but the pulley itself doesn't have any mass, and the pulley itself is not moving. But we have masses moving. We're told that one mass is moving downward, so I let that be mass 2. we're told that it's moving downward with an acceleration that was -3 force g. That tells me immediately that mass 1 has to have a +3 force g acceleration, because the system is accelerating at the same rate. The rope isn't stretching or scrunching. We ultimately need to solve for mass 1. To do so, we did 2 free body diagrams. We did one free body diagram for mass 1, where we considered the force of gravity acting downward on it and the tension of the rope, which we called T1 for the part of the rope acting on mass 1. We then did a free body diagram for mass 2. Similarly, it's got force of gravity acting down, tensional force acting up. We called that T2, but this was the key. When you have an ideal rope or an ideal string, tension is preserved throughout. So while T1 is the tensional force that's happening at where the rope touches the mass right here, and T2 is where the rope is touching mass 2, that tension is preserved throughout, and that licensed me to say T1 equals T2. And so then all the math that you see in black, I was able to use how I expressed T1 and T2 to then have some more simple algebra where I just have masses and some fraction of gravity. And that allowed me to solve for the fact that mass 1 is 1/7 the mass of mass 2. Since we're given mass 2 at the beginning, then we just simply divide that by 7 to get mass 1. And so that concludes problem number 5 from problem set number 4. There'll be a problem exactly like this on an upcoming exam. This is problem 9 on problem set 4. There will be an exam problem exactly like this. If you can imagine, we're looking down on a turntable, and the turntable is rotating in a clockwise direction as symbolized by the green arrow. And then you can imagine that there is a metal cylinder, and that metal cylinder is sitting on the turntable, and it's stationary. As the turntable turns, the small metal cylinder does not slip. Let's write down a couple more things. It's always good to write our parameters down first. We are told that the mass of this small metal cylinder is equal to 0.20 kilograms. We are also given a coefficient of static friction, which in this case, if it's not slipping, it means it's not moving, and so we're talking about static friction keeping it from moving. If it started moving, then we would have to talk about kinetic friction, but we are going to assume that it's not slipping in this problem. The coefficient of static friction is equal to 0.080, and coefficients of static friction as well as coefficients of kinetic friction are dimensionless. We are also told that if you can imagine, this dot right here is the center of the rotation, then we've got a distance to the object that is a distance r. And so the radius of rotation, if you will, is equal to 0.15 meters from the center of the turntable. This problem has multiple things going on. This problem has rotational motion. This problem has circular motion, and which is to say, when I say rotational motion, I'm talking about how we can adapt linear kinematics to rotation. But then when I talk about circular motion, I talk about how if something is going to stay in circular motion at some constant radius r, then we know that the acceleration that is keeping it in the circular motion must equal v squared divided by r, where v is the linear velocity squared divided by the distance from the center of the rotation. So we've got both rotational kinematics, but then we also have centripetal acceleration. And on top of all of that, we also have to think about friction, because it turns out that it's friction that's supplying the requisite centripetal acceleration. To do all of this, I think it might be helpful. So right now, imagine we're looking down on the turntable. Imagine that we were instead looking at the side of the table. So imagine we brought our eyes down to the level of the turntable, and now we're looking at the side. And so we would see an object, and this object we can think of as having both horizontal and vertical forces. Let's do the vertical forces first. The mass that's sitting on the turntable, because it has mass, is going to have a gravitational force acting on it towards the center of the earth. However, the turntable gets in the way, and so we have an action-reaction pair. And so the normal force is the force of the turntable pushing back on the object when the object is trying to accelerate towards the center of the earth because of the gravitational force. So in this particular case, the sum of our forces in our y direction, where let's do our positive x, positive y. So up is positive y, right is positive x, down is negative y, left is negative x. The sum of our forces in y would be equal to the normal force minus mg, because mg is down, and that would be equal to 0 because there's no movement in the vertical direction. The velocity in the vertical direction remains a constant 0, and so if there's a constant velocity, it means there's no acceleration, because acceleration is a change in velocity. This means that the normal force is precisely equal and opposite mg. So we know that for the vertical direction, we have the force of the turntable on the object being equal to mg pointing back up. This is going to be important in a minute, because when we talk about friction, we have to think about both the nature of the surfaces rubbing against each other, and that's what the coefficients tell us, but we also have to think about how hard the surfaces are pressing against each other, and that's what the normal force tells us. So now we, again, imagine our eyes are at the level of a table, looking sideways at the turntable. What we are seeing is an object that's going around in a circle, but there needs to be some centripetal acceleration towards the center of that circle that keeps the object moving in uniform circular motion. That turns out to be a force going in this direction towards the center of the circular motion. You can think of it, if I was to draw it on the aerial view where we're looking down, that force is going to be acting towards the center of the uniform circular motion. And it turns out that it's not like if you're having uniform circular motion, there's some magic force called the centripetal force. It just happens to be that forces that may or may not be allowing circular motion to take place happen to be in a situation where they are, in fact, acting towards the center of a rotational trajectory, which is to say there's not like a centripetal acceleration and a centripetal force in and of itself. It's that other forces of the universe sometimes act as a centripetal force. Like if I was taking an object and I tied it to a rope and I twirled the rope around so that the object was doing uniform circular motion, there is a centripetal force, but it's the tension that supplies the centripetal force. It's not the centripetal force supplying the centripetal force. It has to be an ordinary force just happening to act in such a way that it is oriented towards the center of the circular trajectory. So in the example I just gave, it was tension that was supplying the centripetal force. In this problem, now the rotation, right? The rotation is happening in the x-plane. So certainly it's not the normal force and gravity that are supplying any centripetal force. They're perpendicular. So the only force that we are going to think about here because we're not told about any other external forces. It must be the force of static friction between the object and the turntable that is allowing it to continue to move around in uniform circular motion and not slip. So when we talk about static friction, this is an inequality. It has a maximum value that is equal to the coefficient of static friction multiplied by the normal force. Now again, this term right here is going to be different for different materials, because you can imagine different materials have different levels of smoothness or roughness. But it's one thing to know what the nature of the material it is, and it's another thing to know the nature of how the materials are pressing together. And with a normal force, they're going to be pressing together more. So you have to take into account both of those. We already solved for our normal force with the y part of our free body diagram. So I can extend this relationship to say that this is less than or equal to the coefficient of static friction multiplied by mg. Again, it's an inequality. There's a maximum value. The maximum value is mu s mg. However, the static friction can be less. It just has an upper limit. And at that upper limit, if it has an opposing force, and that opposing force exceeds this maximum, mu s mg, the static friction now is no longer going to be able to overcome the opposing force, and the object's going to start to slip. No more static friction once you exceed the maximum. However, if you can imagine, if there was an opposing force that was less than mu s mg, then certainly the static friction force has enough to be equal and opposite. So it's not that the static friction force is always the maximum. If there's a force that's opposing it, then you have an action-reaction pair, and the static friction is just equal and opposite whatever the opposing force is. That opposing force can continue to strengthen until you get to the maximum limit. And once it exceeds the maximum limit, then the static friction force can no longer oppose, and then you get slipping. So in this problem, we are looking for a maximum velocity that this object can spin around. So this is an example where we're going to put the static friction to the limit, right? We are going to look at when the static friction is maximum, what the velocity is moving about the circular trajectory, such that if the velocity got any more, then the requisite centripetal force would be more than the maximum threshold for the static friction. The static friction could no longer supply the requisite centripetal force, and you begin to slip. I've mentioned centripetal force a couple of times. I want to be more explicit about it now. The centripetal force, A centripetal, is equal in uniform circular motion to the mass that's going about the circle multiplied by the linear velocity divided by the radius of the circular trajectory. So just to be clear, if I have a circular motion and I have some object, and that object is going around in a circle, then there must be some centripetal force acting towards the center of the circle, where the centripetal force is equal to the mass times the centripetal acceleration, which is equal to, the centripetal acceleration is just v squared over r. I got one step ahead of myself there. I conflated force and acceleration. So and centripetal acceleration is just the linear velocity v squared divided by r, which is the distance from the center of the rotation to where the object is rotating. The centripetal force is the mass times the centripetal acceleration, and so this equals m, and then here's where that v squared over r that I just wrote over on the left. So this is what is required. It's not like this thing called the centripetal force just shows up and says, I'm here to cause uniform circular motion. We have to have existing forces that happen to have the magnitude mv squared over r and happen to be acting towards the center of the circle. And that's what's happening in this problem, where it's the static friction that happens to be acting towards the center of the circular trajectory. And remember, we want to know how high can this value v go, which is to say this is going to require the maximum static friction, which is to say that the centripetal force necessary when we are using static friction to supply it is going to be equal to the coefficient of static friction, mg. This is the maximum amount now, okay? And that static friction is what supplies the mass times the velocity squared over r. It's the static friction maximum that is supplying the requisite centripetal force when v is at its maximum. If this v gets any bigger, the maximum static friction won't be able to do the job anymore, and the object is going to start to slip. So we want to figure out what's the maximum velocity before this object starts to slip. So before I finish this, just to review, we started with a bird's eye view looking down on an object that's rotating on a turntable. Then we lowered our eyes to table level so that we could see that the vertical forces, right, which are perpendicular to the rotation, they're equal and opposite. That allowed us to solve for the normal force, which is just equal to mg. That's going to come in big when it comes to figuring out friction. I talked about the coefficient of static friction and how it's an inequality and it has a maximum value, and that it's the static friction that is supplying the requisite centripetal force in this problem. I talked about how centripetal force is mass times the centripetal acceleration. The centripetal acceleration is equal to v squared over r, where v is the velocity of the rotation and r is the distance from the center of the circular trajectory. And because of Newton's second law, F equals ma, the centripetal force must be mass times centripetal acceleration. So that's why the term in orange you see here as well. So I know that it's the static friction force that's supplying the centripetal force. I know the static friction force has a maximum. So at that maximum is going to be what the V maximum is. If V gets any bigger, the static friction force can't do a job anymore and it's going to start to slip. So that's what got me to the equation you see here on the bottom. And now I can simplify because I have a mass in both cases. And what I want to do is I want to solve for v squared. So what I'm going to do is I'm going to multiply both sides by r such that I get v squared equals mu s g r. And because I have a square term, I need to take the square root of both sides to solve for v, such that I have v equals square root of mu s g r. I have mu s, I have r, and turns out mass doesn't matter in this problem, but g is 9.8, so that would allow me to solve for the velocity. And again, this is velocity max. If this velocity got any more, then this side of the equation would be bigger than the maximum static friction, and so the static friction wouldn't be able to supply the requisite centripetal force and you would have slippage. By the way, this v is linear velocity. Remember, when we have a circle and we have some angle theta, then we talk about the arc that is swept by that angle theta, and we say that S equals r theta, where theta is the angle that's swept and r is the distance away. And so this just simply takes that little circular bit and maps it onto how much linear distance is covered. We can also then think about, well, what is ds dt? That's the time derivative of the arc length, and that's equal to r d theta dt, which we call r omega. So just like we map r theta onto linear distance, we map r omega onto velocity. And so the key move here is that I solve for the linear velocity, which is this right here. But I could also think of it in terms of angular velocity omega. So for instance, if I was asked what's the maximum angular velocity this object could rotate at before it starts to slip, then you would just simply take the linear velocity that we solved for and divide it by r. That's the relationship between the linear velocity v that has shown up in these equations and the angular velocity omega. So just one more overview. When you're talking about rotational motion, you have to have a centripetal acceleration equal to v squared divided by r, which is to say you have to have a centripetal force by Newton's second law that's equal to mv squared over r, mass times the centripetal acceleration. The centripetal force is not a force unto itself. It's not like some special force in the universe that just shows up to make circular motion happen. It's forces that we've already encountered that just happen to be oriented in a situation where the acceleration is pointed towards the center of the circular motion. For uniform circular motion, we have some linear velocity v that the object is traveling about in the circle, and we have some distance away from the center of the circle. We need some force to step in and do the job of supplying the requisite centripetal force. In this particular problem, it's the static friction that is supplying the requisite centripetal force. When we talk about static friction is actually an inequality. If there's a little bit of force acting against static friction, well, because of an action-reaction pair, the static friction is only going to offer equal and opposite of whatever that little force was. If that little force gets bigger and bigger, static friction is going to get bigger and bigger up until a threshold. At the threshold, that's the most static friction can offer equal and opposite. And if the opposing force gets bigger, static friction can no longer do the job and it starts to slip. So in this problem, if we want to figure out what's the maximum velocity that this small metal cylinder can whiz around on a turntable, we're going to test the limits of the static friction. We're going to set the static friction to its maximum. And remember, static friction is both the nature of the surface and the degree to which the surfaces are pressing together. So you need to know both the coefficient term for static friction, but also the normal force. We solved the normal force. It's equal to mg. We're given the static friction force for the small metal cylinder. So we know that that must supply the requisite centripetal force. We know that centripetal force is equal to mv squared over r. So I equated the mu static mg to mv squared over r. Mass is canceled, so it turns out the mass doesn't matter in this problem, and we were able to get an expression for v in terms of the square root of the coefficient of static friction multiplied by g multiplied by r, where one more time, r is the distance from the center of the circular trajectory. And then just to close, I showed how this linear velocity v is related to the angular velocity omega, so you can translate between one or the other based on how the question is posed. Hope you found this useful. This concludes question number 9 from problem set number 4.